It's recording. All right. So before I have a moment, okay, I'm sharing my screen. I'm not on mute. That's all we can ask for, I think. Okay. So we'll do a little bit of review. Sorry. And then today we're going to finish 2.1, which is numerical data, right? And then I'm going to save 2.2 for next week, which is categorical data. All right, a little bit of review. Sorry, my fingers they're giving me grief. A little bit of review. We talked about distributions, the shapes of distributions, right? And so today we're going to focus on unimodal distributions. So today we're going to talk about unimodal distributions, so one peak. But of those unimodal distributions, we had kind of three typical options, right? And so we could have a distribution that looks like this, right? Unimodal and symmetric. In fact, it's a specific shape called the normal. Oh, that didn't. So unimodal and symmetric versus, what's the other one that we could have? Skewed, nice. Skewed left in this case. I didn't do very much of a tail. I'll do a better tail on the right skew. I just gave it away, didn't I? Oops. There. All right, skewed right. Skewed in the direction of the tails. And so then what we said last day is, okay, if we have this special case where we have a normal distribution, then the best measures of center and spread that we have are going to be the mean and the standard deviation. So depending on the shape, if the shape is normal, and I'm going to lump these to skewed left, skewed right. Oh, that's sloppy. I actually can't feel this finger right now. So, who needs it? It's just my writing finger. So I'm going to lump those into non-normal distributions. It doesn't matter. Okay. So if I have a normal distribution versus a non-normal distribution, I'm calling it review, which is kind of cheeky because we didn't get this far last day, but I'm also kind of introducing the stuff for today. Then in terms of the center and the spread, this is from last day. If we have a normal distribution, then we're going to use the mean as the center. For the spread, we're going to use the standard deviation. Can't remember exactly how far we got. I think I snuck it in where I said the standard deviation is the square root of the variance. Right, so I'll highlight that again, but for now, let's just accept it as fact. If we're talking about the spread of a normal distribution, we're going to use the standard deviation. Now, I'll do a different color because it's new, but for a non-normal distribution, we're going to use what's called the median. We're going to talk about how to find the median today. And for the spread, we're going to use the interquartile range. That doesn't mean anything right now, maybe, but it will later on. So again, accepting it as fact, okay? Now the problem is, and where humans come in, is we can calculate either one of these for any data, any numerical data. We can calculate the standard deviation. We can calculate the interquartile range always. We can calculate the mean, the median. We can calculate all these things and Excel will just let us, or whatever software we're using will just let us. And so it's our job to know when it's appropriate to use as a measure of center for example, the mean versus the median, right? And so that's our job. Okay. And of course, I'm going to talk about how to find the median and the interquartile range. And that's because we've got paper tests, right? And so we need to be able to do it by hand, right? But usually Excel does it, and Excel does it in a fancier way. They do some moves, right? And so they don't always match up exactly, just as a heads up. But the way we do it in class today is how I expect you to do it on the test. Okay. Tests. Who needs them, right? Okay. So going back to last day, we introduced something called a statistic. A statistic was a measurement from the sample, right? So a measurement that you've calculated from a sample versus a parameter is a measurement that you've taken from the population. Now, it's unlikely that you'll ever be able to do that because we rarely have the entire population, right? But we introduce things like the mean, right? And the notation for the mean. The notation for the mean, if it's from the sample, was X bar, right? Anything with a bar over it indicates a sample average. Okay? Then we said, okay, fine, but I also need to be able to talk about the average of the population. So then we use mu, capital mu. It just struck me, I don't know what lowercase mu looks like. Probably just a mini version, I think. I don't know. But then we introduce the variance. And the variance, if it's from the sample, we use S squared, lowercase s squared. And then if it's from the population, we use sigma squared, so a lowercase sigma squared. And then I feel like I remember kind of sneaking it in last minute, right? But the standard deviation, I'm just going to scoot this over just a bit, is the square root of the variance. Okay. And so if I take the square root of s squared, I end up at s. I ignore the negative option, right? If I take the square root of a value, it becomes plus minus the result, right? Technically. But because I'm talking about spread, I can never have a negative spread. There's no way to imagine a negative spread, right? And so it's always positive, so we just ignore that. But same thing for sigma squared. If I take the square root of sigma squared, I end up with sigma, right? And so we can calculate the standard deviation by taking the square root of the variance, right? And we outlined all the steps that we can take to calculate the variance from the formula, which I think I kept here from last day. Okay. Of course, we're going to use Excel to calculate the variance and the standard deviation and all those things. But the key part of calculating the variance, well, one, it was to be able to look at a formula like this and not be terribly scared, right? You can break it down and you know what to do. I'm not going to get you to do a calculation like this on the test, right? Maybe on an assignment, just to have you try it, right? But you don't need to calculate the variance. I'll give it to you if you need it. But what's the first thing that we did? Well, we had to find the mean, because the mean is here in X bar, right? So that's your first step, step 0, I guess. And then we take the distance that each value is from the mean, right? And so the deviation from the mean. Some of them are positive, some of them are negative. We squared those to get rid of the negatives, but also to amplify large deviations. And then we add those all up. This becomes one number, right? That number is divided by n minus 1. Okay? And so I kept these notes in here from last day. And just as I remembered, right, I snuck it in at the very end. The variance is s squared, and so the standard deviation is the square root of the variance. Now, I said this last day, so I'll include it as part of the review, but right, we use the squared deviations to get rid of the negatives. That's a common thing that we use squares for, okay? But also because larger deviations are weighted more heavily. Okay? So if we have a deviation of 1 versus 2, right? So a data point is 1 unit away from the mean, right? That's a deviation of 1. So now if I square that deviation, deviation, right? Then I get 1 squared is still 1, right? And notice how I increased by 1 here. Doesn't matter what the units are, but I increased by 1. And so then when I take my squared deviations, what we mean by amplifying that distance, 2 squared all of a sudden is 4. So I've increased my deviation by 1, but now all of a sudden I'm penalized by 4, right, instead of 1. And so here resulted in an increase of 3. So that's what I mean when we say we penalize those large deviations. So large deviations are penalized. There. I'll call that the end of our review, although I sprinkled in some new things, kind of like a coming up / what we've done before. Okay. So we saw the standard deviation. If you're calculating things by hand, you would need to find the variance first and then take the square root, but then that's easy enough, right? And so if you found that the variance is 4.11, for example, right? Then if you want to find the standard deviation, you can take the square root of that and you find that it's 2.03 hours. Now, one thing I wanted to highlight here is that s squared was 4.11 hours squared. So the reason that we use the standard deviation is because the units are on the same playing field as the mean. It gets difficult to wrap our head around hours squared, right? Squared units are hard to deal with. So in all introductory courses, we usually just talk about the standard deviation. That's fine. We're okay with that. Potentially even happy with that, not having to talk about units squared. Yeah. And so this is kind of foreshadowing, but we'll see that all the data are within 3 standard deviations of the mean. Okay, so that's kind of a fun property. Okay? We will find that most data fits within 3 standard deviations from the mean, but we're not going to see that again until I think it's chapter 4 or something. But now you know. So we talked about the mean, we talked about the standard deviation or the variance a lot, and then we said, well, then you just take the square root and there you have the standard deviation, right? And the standard deviation is a measure of spread if you have a normal distribution. So now what if we don't have a normal distribution? So if we have a non-normal distribution, I should capitalize it. You don't have to, but helps. If we have a non-normal distribution, we use the median as the center. Okay. Now the median is the value that splits the data in half, which means that you have to sort your data first, right? Otherwise you would just be finding some random point in the middle, right? And so first thing you want to do is you want to sort your data. 1, sort the data. And then 2, there's all these kind of things that you can do, official things that you can do. But I like to use my patent pending boop, boop, boop method, where I just take my fingers and then I boop, boop into the middle, because it is just the midpoint. We're going to have such small data sets that we're working with when we're doing it by hand that it's the easiest way to do it. And so I like to put my fingers here on the outside, and then I boop, 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 boop. And so anyone who wasn't here is going to say, boop, boop, boop doesn't mean anything to me. That's okay. I don't know how else to say it. I call it my boop, boop, boop method to find the center. Yeah. Now there are 2 scenarios. So in the first scenario here in this tiny, tiny data set, right, we landed on a value. Okay? So then this value of 2 is the median. Okay? Now, right, so here we landed on a value, which is the median. Okay. Ugh. We landed. Whereas if there are an even number of observations, then the median is the average of the 2 values in the middle. Okay. Fair enough. Right. Relatively straightforward stuff. The reason I highlight that is because later, when we find the quartiles, yes, we do more, then how we find those that is determined by how we found the median. So in this case, right, if there are an even number of observations, then, so in this case, I'm starting my boop, boop from the outside, boop, 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 boop. And I land on 2 and 3 at the same time. So then, I mean, unless, don't think about it too much, because to find the median, in this case, we take the mean of the 2 values. That's confusing, right? But I think it's what you would end up doing intuitively. You land on 2 things. What are you going to do? Well, take the average. Seems reasonable, and that is exactly what you do. So to indicate that that's what you're doing, what we do is we draw a line down the center, right? And I only do that as a reminder later that that line is where I'm pretending the median is. Okay? So here I would write the median is 2.5. I'll do a bigger example in just a little bit, but we've got some terminology here. So you've probably heard of percentiles, right? Scored at the 90th percentile. What does that mean? It means that 90% of the scores were below that value, implying that 10% were above, right? And so you don't want to say something silly like the 5th percentile, because what does that mean? Oh, I scored in the 5th percentile. Oh, I hope not, right? That means that 5% of the scores were less than yours, implying 95 or higher than yours, right? So you want to be careful when you use the term percentile, because I hear it used improperly sometimes. But the 50th percentile is the point where 50% of the data is below it, which is exactly what we found here, right? At this line, I have 3 values below, implying 3 values above, right? Because it's the middle point. So any percentile is going to be whatever the percentile is has that percentage below that point, and then 100 minus that percentile above it. And so the median is the 50th percentile. Now, as a way of introducing the quartiles, I'm just going to introduce them by definition of the percentile, and then we'll talk about them, and I'll show you how to calculate them. The 25th percentile, right? Going back to the definition of the percentile, says that, okay, 25% of the data is below this point. Okay, and so we call that the first quartile. What have you done? Really, you've split your data into quarters, right? And so if we imagine kind of a minimum to maximum number line here, right? What do you have? You have your median has 50% below it, 50% above it. Wow, that's annoying. The portables, right? If you had to split this into quarters, even if you didn't really know what to do, if I asked you, hey, where's the first quartile? You think about kind of what a quarter is, and you say, okay, well, if I've split it in half, how about I split the lower half in half? That's exactly what you're going to do. So Q1, right, has 25% of the data below it, right, because you've cut it into quarters. And technically the median is the second quartile, but we don't call it that usually, right? Or Q2, the second quartile, because we have a more specific term for it, which is the median. Is it a nice car at least? No. Who parks out here anyways? It's weird. How about the third quartile? I think we've got the idea now. Now I've lost my rhythm. Beep, beep, beep. How about here? 75th percentile, right? Third quartile. So now I've got 3/4 of the data below this point, and I've got, well, the remaining quarter above this point, right? So here's my Q3, right? The third quartile. Okay. And who knew it'd be so soon that we would talk about the interquartile range, right? It was mere moments ago that I said, we don't know what this is. Don't worry about it. Just relax. Well, bye-bye. The interquartile range is the distance between Q3 and Q1. Yeah? And so it's the distance of the middle 50% of the data. Right? And that's just by definition, right? And so the distance between Q3 and Q1 is this part here, right? But if we've split things into quarters, then really what we're talking about here is the middle 50% of the data, right? Got them all into quarters. Okay. So let's see here. The interquartile range is abbreviated IQR. And so here, the interquartile range is the IQR, and it's going to be on your formula sheet, which I probably should have brought today, but I totally forgot. Sorry. Save it for next week. Q3 minus Q1. We do Q3 minus Q1 because if we did Q1 minus Q3, then you'd always have a negative number, and that's annoying. Who likes negatives anyways, right? And so we do Q3 minus Q1 to find that distance. Okay, now let me take a sneak peek here, because this, or do I play it cool? Usually I like to take it a different direction here. And you know what? Yeah, let's do it. We don't know what you're talking about, Emily. I know, that's okay. So here, one of the main things that we use the interquartile range for is to find and identify outliers in our data. Okay? It is the measure of spread if you have a non-normal distribution. So let's just highlight that, because that's good to have just to remember, right? So this is going to be our measure of spread for non-normal distributions. So we use the median as the center and the interquartile range as the spread. But another reason we need the interquartile range is because we need it, like I said, to identify outliers. We also need the IQR. Oh, my R's aren't that nice. There we go. Oh, that's real nice. So we also need the interquartile range to be able to identify any outliers in our data set. So what I want to do is just introduce a couple of examples and do the full workup, and then the following slides do the same thing over again, but I like my way, so I'll kind of breeze through them. But they're in there if you don't want to write out everything I'm writing yet. Okay, so how are we going to identify outliers? Okay, so if we go back to, well, let me just copy it, because I can. It's cheating, I know. Paste. What we're going to say is that as a rule, there we go. Now I've got my rhythm back. This distance is the interquartile range. Right? And so as a rule, and it's called Tukey's rule, it doesn't matter. There are lots of different rules, but what we are going to use and what's most commonly used is called the 1.5 IQR rule. And so the 1.5 IQR rule says that any values more than 1.5 times the interquartile range, and I'll write it down, but I'll say it first. So any values more than 1.5 times the interquartile range away from the quartiles, are considered outliers. Okay, so I'll write that down. Any values beyond 1.5 times the interquartile range from the quartiles are considered outliers. Now it's nice to have a hard and fast rule of how do you determine if you have outliers, right? We can look at a data set and we can say, I suspect that these are outliers, okay? And so this rule says that, well, because we have values beyond these points, then those are considered outliers, right? So it's just nice to have a rule that we can use. Okay? And so notice how I said beyond 1.5 times the interquartile range from the quartiles, right? So so from Q1, where would our outliers be? Well, it would be on the lower end, right? And so then what we're going to do is we're going to find a lower bound by taking our Q1 minus 1.5 times the interquartile range. Okay? And then any values past that point are considered outliers. Okay? How about on the upper end? From Q3, if I'm allowed to go as far as 1.5 times the interquartile range away from Q3, right, then I'm going to be adding to Q3, whereas from Q1 I was subtracting, right? So just a subtle difference in the calculation, right? But I'll put it here, put her there. The lower bound, right, is going to be Q1. And you can kind of talk yourself through the formula. It is on your formula sheet, but you don't really need it there if you kind of know conceptually what it is you're doing. But you're from Q1, you're allowed to move down 1.5 times the interquartile range. Anything beyond that is considered an outlier. Okay. Any values below this point, or I'll say smaller than this, smaller than the lower bound, is an outlier. Oops, outlier period. How about the upper bound? We already developed it, and so we said, so the upper bound, sometimes it's called the fence, but I call them bounds. I'll add it here though in case you're reading something else and it says fence. Q3, so from Q3 I'm allowed to move up, so plus 1.5 times the interquartile range. And so the 1.5 is completely arbitrary, but that's the rule that we use. You could use 2, you could use 2.1, that'd be weird, but you could use lots of different values, but the one that we use is 1.5. Yeah. I'm going to highlight the differences here, right, because you're moving away from your quartiles. So then, any values larger than the upper bound are outliers, potentially plural. I don't know why I strayed from the same format. I did. I don't know. Pick whichever one you like better. It went from plural to singular, so that's not great. That's all right. I think you get the idea. What if I change it to any value smaller than the lower bound is an outlier? There, fixed it. I'll do the same thing. Any value larger than the upper bound is an outlier. Now they're matchy-matchy. Whoops. Okay. So usually how we summarize things like the quartiles, the median, is in a 5-number summary. Okay, so on test 1, I'll definitely ask you, find the 5-number summary. Okay, well, what's the 5-number summary? So we summarize the quartiles slash, I guess, the data overall slash data using a 5-number summary. Now a 5-number summary. Now let me just 1, 2, 3, 4. I obviously need 5 lines, so I'm going to give myself 5 lines. 5-number summary starts from the minimum. So what's your smallest value? Then you move through Q1, then the median, Q3, and then the maximum. You have to list them in this order. Okay. I guess in theory you could go from the maximum to the minimum, but that is weird. So it must be in this order. The reason is, in theory, the 5-number summary is supposed to help us figure out what the distribution of the data looks like. Now, our brains don't really work great for this type of stuff, right? If we have a minimum of, and I'll just grab, oh, you know what? Let's do a bigger example, actually. I'll add a page. Let's do a proper example. Huh? Consider the data now. I'm not very good at making up data, but let's go for 2, 5, 3, 7, 9, 2 again, why not? And maybe 6. I don't know, whatever. First thing, well, this isn't sorted, right? And so what we want to do is we're going to find the 5-number summary. Maybe I'll put it down here. Part A, find the 5-number summary. Okay. Well, the 5-number summary, we just said, is the minimum, Q1, the median, Q3, and the maximum. So we haven't done any practice finding the quartiles, but I'm confident that you can do it, and we'll do it together. And so asking for the 5-number summary seems innocent enough. It's actually quite a bit of work, right? So first thing you have to do is you have to sort the data. So we want to sort the data and I always count how many points I have, just so that when I rewrite it out, I have the same number of points at least. And I also try to check them off as I list them, right? Because my answers hinge on me writing down the right answer or right values, right? And so I've got done 2, and then I've got another 2, and then I've got a 3, and then I've got a 5, and then I've got a 6, then I've got a 7, and then I've got a 9. Let's check. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Nice. Feeling confident that I got them all. Okay. And they're now sorted. Okay. So first thing I'm going to do is I'm going to find the median. And so start on the outside, and I'll do it on the board here. And don't go cross-eyed. Boop, 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 boop. And I feel like I land on a value. Boop, 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 boop. Boop, bing. So then the median is 5. Okay? Now, the rule for finding the quartile says that if you have used the value as the median, which we have in this case, then you don't use it to find your quartiles, right? So now 5 is the median. So then to find your lower quartile, you're going to start at 3, right? That's going to be different from where we take the average. So I'm going to add an example of that as well. Okay, so we'll have kind of 2 examples, and then we'll pick one that we like. Okay, so then to find the quartiles, I'll say since the median is one of the numbers, we don't use it in finding the quartiles. But if I asked you, okay, I told you how to find the median, now find the quartiles, right? Just knowing that piece of information that you're not going to use the 5, right? I'm feeling pretty confident that you would say, oh, okay, maybe it's the median of the lower half, and then the third quartile is the median of the upper half, right? You just zero in on the lower half and then the upper half, right? And so from here, you'd be exactly right. The first quartile is 2. Now, on the upper half, same deal, right? You're not using the 5. You want to use the 6 and the 9. And so Q3 is 7. It's obviously not life or death if you're using the 5, or if we actually wanted these values for a large data set, then you would use Excel, right? And Excel is going to do some weighting in the background, so they make a fancier median quartiles, and so they're not quite going to match anyways. But for your assignment questions, it's assuming that you're doing it this way, right? And so that's why I need to tell you. But also on the test, this is what I'm assuming and expecting you to do. Follow the rules. Okay, so our 5-number summary here is, well, it was the minimum, right? The 5-number summary, I'll just copy here. Once we have sorted data, finding the minimum and the maximum, those are gimme marks, right? And so the minimum is 2 and the maximum is 9. I like to do those right away. And there have been times where I've been marking and the minimum and the maximum were left blank. What? Don't do that, okay? You can do it. I like to start at the median because it's the first thing that I found, but anyway, we'll do. The median in this case is 5, and Q1 was 2, and Q3 was 7. It doesn't mean much in this scenario because we've got a very small data set, but when I say that the minimum is 2 and Q1 is 2, right, they're very close together, but I also know that a quarter of the data happened in this distance, right? So of course, if I have a larger data set, then that's valuable information. It tells me that, okay, a lot of points happened between 2 and 2, right? We're 2. And so we use these distances, or we can use these distances to determine, okay, if there's a long distance between Q1 and the median, right? What does that tell me? It tells me that it took a long time to span that quarter of the data. right? Which translates to not very high bars, right? Took a long time to get a quarter of the data, right? So a short distance means that there's lots of data there, or in that short distance. And then a longer distance is the data is more spread out because you cut it into quarters, right? And so, all right. So now, part B of this question. So we found the 5-number summary. Hooray. Now, on the test, so A is going to be find the 5-number summary. And I promise it will be like this. Part B is going to be, are there any outliers? Uh-oh. Are there any outliers? Okay. Outliers, you're probably thinking 1.5 IQR rule, and you'd be correct, right? But what does that mean? It means that I need to find the interquartile range first, right? And so let's start there. The interquartile range is Q3 minus Q1, which in this case is 7 minus 2. Right? I can grab them from just above. So 7 minus 2 is 5. Now I have to do it just to make sure, and then 1.5 times that, just so I have it, and you'll have it. And then to find if there are any outliers, what am I going to do? I'm going to say, well, I'm going to find the lower bound and then the upper bound. So the lower bound is Q1 minus 1.5 times the interquartile range. Q1 is 2 minus 1.5 times 5. 1.5 times 5 is 7.5. So I get 2 minus 7.5. You don't have to show that step, but I want to do it here because I want to emphasize bed mass, right? You have to multiply before you can subtract it, which is one of the more common things that happens, right? You want to multiply these before you take them away from 2. And so 2 minus 7.5 puts me at negative 5.5. And I'm going to add another page here. So then what I'm going to do is, in my data set, which I have sorted already, I'm going to copy it down here. Mostly because I can. So then how I like to do it is I like to, well, this is on a number line, right? We sorted them, so they're increasing. And so what I can do is I can place negative 5.5 on this number line. And so what I can do is I can try to place this, and it would fall somewhere here, negative 5.5. So then I can visualize that there are no values beyond this point, right? Which means there are no outliers on the lower end. So here, what I want you to say / require you to say is, since there are no values smaller than negative 5.5, there are no outliers on the lower bound. We still have to do the upper bound, but there are no outliers. There are no outliers on the lower bound. Maybe I should say lower end. There. Just so I don't say bound, lower bound twice, basically. Okay. Now we do the same thing for the upper bound. All right, we calculate the upper bound. is going to be Q3 plus 1.5 times the interquartile range. And we've already calculated the 1.5 times the interquartile range. As long as you've shown me what you did once, you can just plug in 7.5 if you want. I'm going to show the work just so that you have something to refer to. Q3 is 7 plus 1.5 times 5. So 7 plus 7.5, 14.5. Okay. So now I do the same thing again, but to kind of save some space here, I'm going to take this value and I'm going to draw it up here instead. Just on the same number line. Oh, this doesn't look very good. There. So here I have 14.5. You have to do all this work only to tell me that there are no outliers. Oh man, I know. So then, right, there are no values beyond 14.5. In fact, you could take it as far as there are no values beyond 9, right, which is less than 14.5, but you always want to talk about the 14.5. So I'm just going to say, since there are no values larger than 14.5, there are no outliers on the upper end. So now, right, remember we said, well, this was the case if I land on a value and I use it as the median. And so now I just quickly want to run you through the scenario where we take the average, because finding the quartiles is just slightly different, because now I'm not using a value as the median. And so that dictates how I'm going to find the quartiles. Copy. And did I? Okay. No, I didn't. What if the median was the average of two values? Is the average of two values. I'll remove all these. And then, how about I do something even funner? Just tack on a 50 at the end. Why, you can't do that. Yes, I can. Do whatever I want. Is it going to affect the median greatly? Sort of, right? But not as much as it would affect the mean, right? The mean of these values would be pulled towards the 50, right? But for now, we're just talking about the median. And so now, here we go. Find the, okay, fine. I'll write out. Find the 5-number summary. And maybe I'll bump these down just one more so I can copy them more cleanly later. 5-number summary. Boop, 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 boop. We've sorted them already, so that's good. Boop, 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 Boop. Whee. I circle the two values, right, just to indicate that I landed on both of these. Okay. And then again, we draw a line at the center. Now this line represents the median. Okay. So the median is 5 plus 6 divided by 2, which I'm going to go ahead and say is 5.5. So it did change, right, from 5, but not drastically, right? So now, okay, so we've got the median. We're feeling good. And then the rule is that because I haven't used either of these values, the 5 or the 6, as the median, then I count in from just the other side of the bar, right? So since the bar is the median, since the bar represents the median, we count in from the bar to find the quartiles. Just a subtle difference. And I mean, is it going to make or break you if you're working on a report or something and you did it? Well, you'd use Excel anyways, so it's kind of a moot point. But it's more about being given rules and being able to apply those rules. That's what I'm more concerned about. Following instructions. So now, here at this line is the median. So then if I want to find the quartiles, the first quartile, I'm going to start at 5, 2, and 5. And again, I land on 2 values. So Q1 is 2 plus 3 divided by 2, which is 2.5. Same thing on the upper end. I'm going to start at the 6 and the 50. Q3 is 7 plus 9 divided by 2, which is 8. Okay. Add a page. It's almost like I didn't need slides at all. Okay. So now my 5-number summary, not changed drastically, but changed a little bit. So now my minimum, how? There's only one other portable. Minimum, Q1, the median, Q3, and the maximum. Go for these cheap thrills. Minimum and the maximum. 2, 50. Got those in the bag. How about the median? Right, I like to start there. It doesn't matter. 5.5. Q1 we said was 2.5, and Q3 we said was 8. If I did those wrong, let me know. Nice. So now, part B, are there any outliers? Nice. I'm going to go ahead and say 50 appears to be an outlier, right? But we're going to confirm. So are there any outliers? Well, first thing we need to do is we need to find the interquartile range, which is Q3 minus Q1, 8 minus 2.5, 5.5. Just confirm. And then sometimes I do the 1.5 times the interquartile range just separately, and then I can just use it as a value. It's completely up to you. The lower bound is Q1 minus 1.5 times the interquartile range. Q1, I think we said was 2.5. minus 1.5 times 5.5. Whoa, so many halves. Which is 2.5 minus 8.25. Negative 5.75. Oh, I guess I should show it. We already did it. Paste. So now here, negative 5.75 would fall somewhere here on this number line. Everything's kind of scooped up in that lower bound. And so since there are no values smaller than negative 5.75, there are no outliers on the lower bound. I do want to say that although it seems tedious to write this all out, right, you might be tempted to say something like, therefore no outliers, right? And that's all fine. You know what you're doing, right? But what's your job? It's to communicate to someone else why there are no outliers. And that someone else is me in this case, right? You have to show me that you know why there are no outliers, right? So you don't want to get sloppy and just kind of find shortcuts, right? But as long as you mention what the bound is, right? And why there are no outliers, well, there's no outliers because there are no values smaller than this. This is the shortest way that you could write that, I think. Add a page. How about on the upper end? So now the upper bound Q3 plus 1.5 times the interquartile range. Q3 was 8. And let me just remember, plus 1.5 times, I was just there, 5.5, I think. Yeah. So 8 plus 8.25, gonna go with 16.25. We just had this negative 5.75. And then now, the reason I picked 50, of course, was to show that, okay, 16.25 would fall somewhere between 9 and 50, right? So now all of a sudden, I have an outlier and it's on the upper end. Since one data point, and I'll just show off. It's always nice to show off that data point is 50. Okay. So since one data point is beyond 16.25, we have one outlier on the upper end. Nice. So like we were saying, the distances between these quartiles and in the 5-number summary, we could spend quite a bit of time thinking about what that distribution would look like. Or often what we do is we visualize the distribution with a box plot. And a box plot looks like this. It's got a box in the middle. And then it's got some whiskers, which are kind of cute to think about, right? So here we've got the whiskers, and then what are these showing? If you had to guess, you'd probably say, oh, outliers. Yes, you did it. Okay, so then on the next slide, I've got the anatomy of a box plot. So if you had to draw a box plot, now I don't do that because it's weird. We use software to generate box plots, right? But to read a box plot, the median is at the center. So there's going to be a center line, and that's the median. So you've got your median, and then you've got your quartiles. Because the scale is increasing, going up, of course, then the first quartile, then the median, then the third quartile, and then on either end, we have what we call whiskers. Okay? So I've got a lower whisker and an upper whisker. Now, because I'm not going to make you draw a box plot, we don't have to spend a ton of time here, but the whiskers are drawn to the furthest or the outermost value that's still within the bounds, those upper and lower bounds. Okay, so if I just quickly refer back to this value here, the bounds, the upper and lower bounds are not added to the plot because we're just plotting the data. But what would happen is the whisker would say, okay, my upper bound is 16.25, my whisker would go to 9, right? And then I would indicate 50 with just a dot. Okay? And so, and here, the lower whisker would go to 2, right? It's allowed to go to negative 5.75, but the lowest data point is 2. So then the whisker would be drawn at 2. So then here, these guys are outliers. I've already used all my colors. Outliers by the 1.5 IQR rule or 1.5 IQR rule. Nice. So here, I'm just going to breeze through this because we've already spent a lot of time doing this. Kind of a bigger example. So let's think about, so when I changed, or when I added a data point of 50, right? Intuitively, we all recognize that, okay, that would change my average quite a bit, right? In fact, the average would be pulled in the direction of the tail, right? Or in the direction of the outlier. And so here, the mean is pulled in the direction of the outliers, potentially more than one. Whereas the median is relatively unaffected by outliers. Whereas the median is relatively, it could change a little bit, right? We saw small change, but not a huge change, whereas the median is relatively unaffected by outliers. Oops. And so that's the reason why we use the mean for symmetric data, right? But we have to use the median for skewed data, right? And so here, this is called, we call those statistics robust. So the median and the interquartile range, the median and IQR, oops, are robust to outliers. Right? They just kind of stay steady relatively, right? And they're not swayed by outliers. And so one of the examples now at annual household income, I guess, again, money, it's skewed to the right, right? And so looking at this or even thinking about household income, I know it's going to be skewed to the right most likely, which means I should be using the median and the interquartile range as my center and spread. And just as an example to see how it changes, you have the original data and the mean and the median. Okay, so fine. 190, 245. Notice how the 245 is pulled in the direction of the tails, right? These higher values. And then if we change the largest value to $10 million, right? The median would not change, but the mean would, right? And then if we move the smallest data point, so we take the smallest and we make it 10 million, kind of bump it to the side, of course, the median is going to change just slightly, and the mean is going to change quite a bit. Yeah? And so for skewed distributions, we use the median and the interquartile range. Whereas if you have a symmetric distribution, then being able to use the mean and the standard deviation is great because there are a lot of tools associated with the mean and the standard deviation. But you shouldn't use it unless you have a symmetric distribution. So if you would like to estimate the typical household income for a student, would you be analyzing the mean or the median, knowing that it's money, right? You suspect that it would look something like this, right? So here you've got money, typically. And so what the median would look like, the median would hold steady here, kind of with the lump of the data, where you would just visually put the center anyways. But the mean is going to be pulled in the direction of the tail. Now I'm just drawing these lines. I don't know where they are truly, but I do know the relationship, right? I know that the mean is going to be pulled more in the direction of the tail. Yeah. And so I would use the median and not the mean. Yeah. Because the mean would be somewhere towards the tail. Now, if you have a symmetric distribution, the mean isn't being pulled, well, it's being pulled evenly in both directions. So then, kind of as a fun fact, the mean is going to be relatively close to the median. How could you use that knowledge? If you have numerical summaries, even if you can't see the data, you can look at the values of the mean and the median, and you can determine what the rough shape is, right? Might have to tell you that it's unimodal, and then you can go from there, right? If those values are relatively the same, then it's roughly symmetric, right? Whereas if it's skewed to the right, right, then just kind of imagine this skewed to the right, then the mean is pulled in the direction of the tail, so the mean is larger than the median. Whereas here, if it's skewed left, right, maybe I have the median here, and the median, here I have the mean, here I have the mean. Now the mean is less than the median. So if I give you a distribution like this, right, now we're really good at talking about the shape. Looks like it's skewed to the left. And I would approximate the median to be somewhere here. And then I know that the mean is pulled more in the direction of the tail, right? Because it's being pulled in the direction of the tail. So on that scale, the mean is less than the median. And so I would pick C. Now, just as kind of a fun fact, if you have extremely skewed data, then sometimes you might have to make a transformation or transform the data. And so especially if you're dealing with money data, you'll often be doing a log transformation. Okay. And so you take the log of each value. This isn't something I'm going to get you to do or anything. It's just something to have up your sleeve. Okay. But I want to show you what it does. So you've got the log button on your calculator, log base 10, log base E. Oh no. And there's a typo on here, which I didn't catch. If you're talking about the number of basketball games attended, a huge amount of people have attended between 0 and 10 basketball games. But then there are these diehard fans. So you've got this extremely skewed data. Now the typo is here. If I take the log of each data point, right, now all of a sudden I have a shape that I can kind of wrap my head around and talk about. Yeah. And so, like I said, we're not going to do log or any sort of transformations, but it's just nice to have. Missed it twice. And so if you take the log of 70, it's 4.25. The log of 50, it's 3.91, blah, blah, blah. The reason we're avoiding it is because the interpretation becomes hard, right? Now you have to talk about the log of the number of basketball games that someone's attended, and that gets boggy. So that's why we don't do it in this course, but it's done in real life. And so usually it's harder to interpret. And I'm just going to say money here. There's lots of other skewed variables, but who cares? Heat maps, just kind of a fun numerical data visualization, not something that you need to know about necessarily, but you've got a gradient of colors to indicate what the numerical value is in each county or whatever it is. Nice. Okay, down to the wire, but you did it. I did it. I'll leave 2.2 for next week, but we're also going to be doing and 3.1 next day. So if you're reading ahead, you'll want to do 2.2 as well as 3.1. Have a wonderful weekend. I'll see you on Tuesday.